Hello, and welcome to another exciting episode of Calculus 3 and U. In this video, we'll be discussing Green's theorem, the first in a sequence of important results called the big integral theorems. These are Green's theorem, Stokes' theorem, and the divergence theorem. As we will see, all of these theorems are generalizations of this form of the fundamental theorem of calculus. The meaning of this mathematical statement is that the net or overall change is the accumulation of small incremental changes. The incremental change of a function over a small interval of width dx is the differential f prime of x times dx. Applying the integral to add up all these small changes, we get the net change in the function over the interval. Notice that the fundamental theorem of calculus related the integral over the entire interval from x1 to x2 to a calculation involving only the boundary of the interval. That is, at the individual points x1 and x2. The big integral theorems capture these same ideas, just for different types of integrals and with different notions of small incremental change. For now, we'll investigate Green's theorem in particular, which is stated as follows. Let D be a region in R2 whose boundary C is a simple closed curve oriented counterclockwise. Then the line integral around C of the vector field with components P and Q is equal to the double integral over the interior region D of dq by dx minus dp by dy. For purposes of applying this theorem, a simple closed curve is basically a curve that does not cross itself. It will also be desirable for the region D to not have any holes in it. It's possible to deal with these cases, but additional care is required, so let's just ignore these types of curves and regions for the moment. I claimed earlier that Green's theorem is a generalization of the fundamental theorem of calculus, but at first glance this doesn't look much like it at all. But let's compare. On the right-hand side of the usual fundamental theorem of calculus, we have an integral of f prime over an entire interval. On the right-hand side of Green's theorem, we have a double integral over the entire region of a quantity involving derivatives. Not identical, but definitely similar. Also, on the left-hand side of the usual fundamental theorem, we have a calculation involving only the boundary of the interval. Similarly to how the left-hand side of Green's theorem only involves the boundary of the region. As an example, let's compute this line integral around a curve, which is the outline of a rectangle in the plane. We could parameterize each segment individually and try to compute 4 separate line integrals, then add the results together. This is a little tedious, but certainly we could do it. However, notice the e to the x squared in the integrand. This is going to be problematic when we parameterize, as e to the x squared doesn't have an elementary antiderivative, making it unreasonable to apply the fundamental theorem of calculus. Instead, let's apply Green's theorem with p equals e to the x squared and q equals negative xy. Be careful with the negative sign here. You can think of this line integral as e to the x squared dx plus negative xy dy if it helps. Now let's write out the formula for this particular p and q. There are a lot of ways to mess this step up, so just be careful to get everything in the correct order. On the right-hand side, you have dq by dx minus dp by dy. Now something awesome happens. Since e to the x squared doesn't involve y, this partial derivative vanishes, completely eliminating the difficult term. Then we're left with a simple double integral over the rectangular region, which can easily be written as an iterated integral, here with x values ranging from 0 to 3, and y values ranging from 2 to 4. I think you've got it from here. Just evaluate this double integral from inside out using the fundamental theorem of calculus to get a final answer of -18. Now let's step back for a moment and recognize what we've done here. We started with a very difficult line integral. And using Green's theorem, we're able to instead evaluate a much, much easier double integral. This is a typical use of Green's theorem that you should definitely keep in mind. To see why Green's theorem works, let's first show that it works on a rectangle with x values ranging from x1 to x2 and y values ranging from y1 to y2. Orienting this curve counterclockwise, we can break it into 4 separate line segments C1, C2, C3, and C4. Then the line integral around the entire boundary of the rectangle can be written as the sum of separate line integrals over each of these segments. Now notice that along C1, the y values are held at a constant value of y1, so here dy is 0. Along C2, the x values are held at a constant value of x2, so dx is 0. Along C3, y values are held at a constant value of y2, so dy is 0 again. And finally, along C4, x values are held at a constant value of x1, so dx is 0 again. So, we can simplify each of these line integrals somewhat. Before manipulating these integrals, let's put the p's and q's next to each other for clarity. Then let's get all the limits of integration in the same order. Recall that swapping the limits of integration produces a negative sign out in front. Once the limits of integration are in the same order, we can combine the integrals. When combining the integrals involving p, let's reverse the order of the subtraction so that the term involving y2 is first. Now this part is a bit clever. The difference in each integrand can be written as yet another integral using the fundamental theorem of calculus. For example, for each fixed value of x, we can express the difference p of x, y2 minus p of x, y1 as the definite integral with respect to y of dp by dy. Similarly, for each fixed value of y, we can express the difference q of x2, y minus q of x1, y as the definite integral with respect to x of dq by dx. Replacing these expressions, we obtain two iterated double integrals, both of which are just double integrals over the whole rectangle. Combining these integrals, we obtain the formula for Green's theorem. All right. Now, Green's theorem also applies to more general curves. To see how these are handled, imagine a simple closed curve and tile it with a rectangular mesh. Now imagine integrating counterclockwise around each of these small rectangles. Notice that each interior segment is traversed twice, once from left to right and then again from right to left, or top to bottom, then bottom to top. So, in the integration, these segments effectively cancel each other out, leaving only the segments along the boundary. Taking this to the larger scale, all interior segments cancel, leaving only the segments on the boundary of the larger mesh. This idea of interior cancellation will be used again in future material. You can see that these segments form an approximation of the curve, which would fit even more closely if the mesh had used smaller rectangles. So, the line integral around C is approximated by the sum of the integrals around each of the individual rectangles. Again, the interior segments canceled each other out. Applying Green's theorem to each of the line integrals in the summation, we obtain an approximation of the double integral of dq by dx minus dp by dy over the entire domain. We've been playing fast and loose with these approximations, but if we make the mesh rectangles smaller and smaller, the approximations become exact, giving us the general formula for Green's theorem. Thanks for watching, and be sure to eat your vegetables.